Hello and welcome to part 2 of related rate problems. How do I do my homework? All right, we discussed in the first video on how to actually end the problem. So that part of these guidelines actually comes under here. I taught you how to use implicit differentiation by differentiating each side with respect to time and substituting values if necessary. So what's going to be new in this video? What's new is you're going to have to actually read a problem. And when you're reading the problem, you want to look at what variables will I be using. So let's say that you're going to use an x and a y in the problem. You need to be thinking then that you're going to have a dx dt and a dy dt. You're going to have rates related to x and y over time. So as you're reading the problem, ask yourself, which one of these is the question asking? Does the question want the x, the y? Does it want a dx dt or dy dt? Because if you are trying to find dy dt, that means somehow in the problem you have the ability to find the other given quantities. So if it's asking you to find dy dt, that means you have to be able to produce an x and a y and a dx dt from the problem. So that is the mindset going in. What variables am I going to use? I need a dx dt and a dy dt if you choose x and y. What in the problem? 3 of those have to be given, and 1 of those is what I have to find. A lot of times making a sketch and label helps. The last thing you're going to have to decide by reading the problem is how are you going to construct your equation? All right, most of your equations probably will stem from some type of geometry formula. Volume and area formulas can be found on the inside cover of your book. You can also ask Siri, you can ask Google, you can ask Alexa. Pythagorean theorem is used often, and this is where I'm going to kind of make a decision to kind of bag some of the problems. Some of them in the textbook problems, you just kind of have to figure it out from the picture, but we're not going to do too many of those. Most of the problems we will do will be based on some geometric formula. All right, let's begin. I went ahead and opened up a new note because we have a lot to write for this first sliding ladder problem. All right, I know there's some other slides that are in your notes. We're going to skip those and just kind of go straight to how we do the problems. All right, sliding ladder problem. A 30-foot ladder is leaning against a house. The base of the ladder is pulled away from the house at a rate of 1.5 feet per second. How fast is the top of the ladder moving down the wall? So here what's going on. I have a house, and I have a ladder. The ladder is 30 feet. That ladder is not a variable. The 30 feet ladder doesn't change. It doesn't automatically become a 25-foot ladder when it falls down the wall. It will remain 30 feet. When I read the problem, they're talking about the base of the ladder and the top of the ladder. Well, here is my base of the ladder. Here is my top of the ladder. Well, as the ladder slides, those distances, the distance of the base is going to change, so that's a variable base. I'm going to choose to give that an x. Then the top of the ladder is going to be falling down. I'm going to give that a y. So here is what I'm thinking in my head right now. My variables are x and y. Therefore, I'm going to have a dx dt and a dy dt in the problem. All right, so let's go back. Let's figure out what they gave me. So a 30-foot ladder is leaning against the house. The base of the ladder is being pulled away from the house at a rate of 1.5 feet per second. Friends, that is a dx dt. They want to know how fast, so we'll take the absolute value of whatever we find, is the top of the ladder moving down the wall. All right, so if I want to know how fast they're asking for a rate, that is what they want me to find. So then we have to decide, well, what is my equation that I'm going to use? Well, this is based on Pythagorean theorem. I have a right triangle. Now, this is where some kids get confused. This is really where the make or break part. When I do Pythagorean theorem, remember that the distance from the base, that's changing. So that's going to stay in x. The y is changing. But the 30, I'm not going to put in a c squared. I'm not going to, first of all, if you put in a c squared, you don't have any information to give you that rate. That's because there is no rate. The 30-foot ladder stays 30 feet even over time, so that fixed piece becomes a part of my equation. This is the nuts and bolts of the setup. All right, here we go. So to answer question A, on question A, they tell me that the base is 3 feet from the house. So when I think of my setup, dy dt is what they want me to find. dx dt is still 1.5 feet per second, but x, the base, is 3 feet from the house. All right, we are still using x squared plus y squared equals 30 squared as my equation. But if I'm going to find dy dt, that means I have to know all the information. So I know dx dt, I know x, but I don't know y. This is not a calculus question. In order to find y when x is 3, I get y squared is going to equal 900 minus 9. And that gives me 29.8. Okay, so now I am ready to differentiate. This is where video 1 comes in. This is where I just differentiate with respect to time and plug in my values. So that's why I had you do that yesterday. So here's my equation. When I differentiate that with respect to time, I get 2x dx dt plus 2y dy dt, and that is going to equal 0 because the derivative of any constant is 0. Now I plug in my values. So I'm going to have 2 times x, which is 3. dx dt is 1.5 feet per second. I'll write that in at the end. Plus 2, we determined that y was 29.8. dy dt equals 0. So this means dy dt, I have to subtract that off. I would have negative 2 times 3 times 1.5 all over 2 times 29.8. So when I put that in my calculator, I get negative 0.151. So that means that dy dt is negative 0.15 feet per second. But the question was asking for how fast, so the top of the ladder is moving at 0.15 feet per second. So for part B, it is the exact same work, no different explanation, except we want to now know when that base is no longer 3 feet from the house, but 21 feet. So I'm just going to go through the exact same work and just erase everything that is a 3 and make it a 21. So the picture doesn't change, our equation doesn't change, but here's what changes. Instead of this 3, and since I'm changing the 3, it's going to cause my y to be different, I'm going to make this 3 a 21. So that means, and my dx dt hasn't changed, and I'm still not changing the fact that I have to find dy dt. But what is going to change is my y. Instead of this 3, we need to now make it a 21. So the square root of 900 minus 21 squared gives us 21.4. So that's the only thing that changes in the problem. When I differentiate, that does not change. What changes is the values that I will put in. So instead of that 3 and instead of that 29.8, what changes is I now have 21, and now I have 21.4. All right, so let's see if I have any calculator issues. Typing this in has kind of been an irritating piece here. So I'm going to have -2 times 21 times 1.5 all over 2 times 21.4. And that gives me -1.47. So this is approximately -1.47 feet per second. And remember, it wanted to know how fast, so my answer would be a positive 1.47 feet per second. And that would be the answer to part B. All right, let's do part C. We still have the exact same thing going on. We still have a 30-foot ladder. We still have that dx dt is 1.5 feet per second. But C is asking for a different problem. It wants to know at what rate the angle is changing between the ladder and the ground. So let's draw a picture again. I have a house. I have a ladder. The ladder is 30 feet. This problem is different. They want to know at what rate the angle is changing between the ladder. So here's the ladder. Here's the ground. So this is the angle theta that they want to know. They want to know what is d theta dt. That's what this is asking. So this is not about x's and y's. It's a new type of problem. It's a type of problem where I have theta and they want to know a d theta dt. All right, so this is where you have to use your brain. There's some critical thinking here about what's going on. We know that we had originally assigned the ground to be x and this to be y. We're going to use SOHCAHTOA to create an equation that isn't going to be Pythagorean theorem, but we're going to create a trig equation. Well, in order to do that, while I know you could pick sine, cosine, tangent, cosecant, secant, cotangent, I would probably stay away from cosecant, secant, and cotangent. It makes it more difficult. Now, let's think about what we know. We know dx dt. We know that that is 1.5 feet per second. We do not know squat about dy dt. So I don't want to use anything about the vertical piece. Why don't we just stick with the ground and the 30 foot, because the ground would be adjacent to theta, 30 feet would be the hypotenuse, and so that's cosine. So that's how I'm organizing this. I'm choosing not to use anything about y's or dy dt's because I don't have any information about that. But I do have a dx dt. So when I figure out my equation, the cosine of theta is equal to x over 30. So when I differentiate, the derivative of the cosine of theta is equal to negative sine theta d theta dt. And you can think of x over 30 as 1/30th x. So that's just going to give me a 1/30th dy, bonehead, dx dt. So I can divide both sides by negative sine theta. So d theta dt is equal to 1 over 30. dx dt is still 1.5 feet per second. This is going to be a negative value, which makes sense. As the ladder is moving outward, your theta is going to get smaller and smaller and smaller. But instead of writing it as negative sine theta, we're going to write it as cosecant of theta. So 1.5 hello, negative 1.5 over 30 reduces to 0.05. And if I forgot to put a negative in there, so I don't think that will throw you off. We get negative 0.05. So d theta dt is equal to negative 0.05 times the cosecant of theta. And friends, this is not wrong and this is not bad, but you have the rate of change of theta with respect to time in terms of theta. So this could be an answer. If this was a choice, this is an answer, but you have to know theta. And I realize to some extent this isn't like a quote unquote real life problem, but I don't know that anybody is going to get a protractor and figure out what angle theta is. If we were actually going to do this, it would seem that most people would just get out and measure the distance of the base of the ladder from the ground. So the following information or the following work is really just putting this equation right here in terms of x instead of in terms of theta. I mean, that is a legit answer, but it's the rate of change of theta and you have to know theta. We would probably just measure the distance from the bottom of the ladder from the house in order to figure that out. So let's go back to our picture. All right, we know that this is x, this is theta, and this is 30. Well, don't we know that the cosecant of theta is equal to 30 over y? And you're like, well, crap, what's going on with that? Because I need this in terms of x. You're like, nah, I want it in terms of x. Why are we in terms of y? You guys, we can figure that out. Don't we know that x squared plus y squared is equal to 900? So isn't y squared equal to this, y is going to equal 900 minus x squared? Yes, you get a positive and negative principal square root. However, because this is distance, we only take the positive principal square root. So this gives me that the cosecant of theta is equal to 30 over the square root of 900 minus x squared. So now I can substitute cosecant of theta in for this expression. So I get that d theta dt is equal to, and I am going to go back and rewrite it in terms of its fraction form, negative 1.5 over 30. Then I'm going to replace the cosecant of theta with our 30 over the square root of 900 minus x squared. So then the 30s cancel. So again, to be clear, let me get blue. Friends, that is an answer. It's just an answer where you would have to know theta. This is an equivalent answer that d theta dt is equal to negative 1.5 over the square root of 900 minus x squared, because this is in terms of x. So this formula, if I know my distance of the base of the ladder from the house, this would allow me to find the rate at which theta is, in this case, decreasing over time. All right, friends, let's talk some baseball. Makes me smile, even though today, or was it yesterday, or I don't even know what day it is, we should have had the home opener within the last few days for the Cardinals. So nevertheless, in that spirit, let's talk baseball. So I did show this on the first video. A couple of things if you are not familiar with the game. First of all, that the standard for Major League Baseball diamond is that the distance from each of the bases is 90. So we're going to need that fact when we do the next problem. And the problem is based on, we have a runner at first base and they are running towards second. So let's keep that in mind. We have a runner at first base running towards second. So what's going to happen is that's going to create a right triangle from home to first base, and we don't know how far the runner has gone. And then when we connect that to home, this is how we're going to create our right triangle for that problem. All right, so let's read it. For the baseball diamond in the previous slide, suppose the player is running from first to second base at a speed of 28 feet per second. Find the rate at which the distance from home plate is changing when the player is 30 feet from second base. Ugh. Okay, here we go. So I'm at home. Here's first. Runner is running towards second, and this is how I make my right triangle. So again, this is the player running from first base. So if the player is running from first to second base at a speed of 28 feet per second, friends, that's a rate. That's the rate of the baseball player. So here is what I'm going to do. I'm going to go ahead and I'm going to make X my player. So I'm going to define X to be wherever the player is located, and this will be important for a latter part of the problem. This is going to be the player's distance from first base. That means 28 feet per second. You guys, that is a dx dt. That is a rate of change of the player over time. Next, they want me to find the rate at which the distance from home plate. Okay, so this is my distance from the runner, wherever the runner is at, to home plate. I'm going to define that as y. So the question is asking for a dy dt. So here is the organization playing out in my head. I have x, which is the player's distance from first base. Y is the distance of the player from home plate. So y is the distance from the player to home. That means I'm going to have a dx dt in my problem and a dy dt in my problem. They told me dx dt was 28 feet per second, and they want you to find the rate from home, so this is what I have to find. Now, this is the part that's a little tricky. They tell me that the player is 30 feet from second base. So in this diagram up here, okay, what they're saying is that the player is here and they are 30 feet from second base. But we have to find X to be the distance from the first base towards second. So if this is 30 by segment addition, it would make that X the distance of the player. So the player has run to here. That distance from first base would then be 60 because these have to total to be 90. All right, so how are we going to find y? Well, you have to be careful about how you set up your Pythagorean theorem. It's not x squared plus y squared equals c squared or something. Remember, this is 90. That is fixed. I cannot change the distance from home to first base. So you guys, these are the legs of the right triangle. So I have x squared plus 90 squared is equal to y squared. We know that x, and I have a misprint. I just did something dumb. This should be 60. Again, math therapy, because I don't feel like re-recording this. Math therapy, this x should have been 60, and I had a copy error when I wrote that down. Okay, hopefully we've recovered from math therapy. All right, so x is 60. So y is going to equal the square root of 60 squared plus 90 squared. So that means y is approximately 108.2, we'll call it. Okay, friends, that's the new piece. Our equation is still x squared plus 90 squared equals y squared, and now we are going to differentiate that with respect to time. So I have 2x dx dt. The derivative of 90 squared is 0. And that's going to equal 2y dy dt. Now I substitute in my values. So I'm going to have 2 times 60 times 28 equals 2 times 108.2 dy dt. So dy dt, the rate of change of the player from home plate, is going. So when I take 2 times 60 times 28, all over 2 times 108.2, I end up with 15.5. So what does this tell me? It tells me that the rate of change of the runner from home when he's 28 feet past first base is 15.5. And I don't know, hold on, there was like a dot in there I didn't like, is 15.5 feet per second. Greetings, and here is our next problem. It has to do with this related rate demo when we discussed how granular substances create a conical pile. So example 5 tells us that at a sand gravel plant, sand is falling off a conveyor and onto a conical pile at a rate of 10 cubic feet per minute. Reading the problem right there, this gives me a lot of information. This tells me that it's a rate of change. Furthermore, it is being measured in cubic feet per minute. This implies something three-dimensional. So we're talking about volume. I think that's an important clue because the rest of the problem discusses how the diameter of the base is approximately 3 times the altitude, and they want to know what rate the height of the pile is changing when the pile is 15 feet high. Well, that pile, my friends, is a cone. So to put this together, I need the volume of a cone. You do not have to memorize the volume of a cone. You can look it up in your textbook. You can ask Siri. You can ask Alexa. But the volume of a cone is 1/3 pi r squared times the height. So this is what is going on in my thinking. I have 3 variables. I'm like, oh no. I have volume, I have a radius, I have a height. So that means we have a dv dt, a dr dt, and I have a dh dt. Okay, so let's kind of read the problem and see what's going on. At a sand gravel plant, sand blah, 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 at a rate of 10 cubic feet per minute. So this tells me that dv dt is 10 cubic feet per minute. So this means I'm going to keep V. I'm going to keep this in my formula. Then they tell me the diameter of the base of the cone is approximately 3 times the altitude. Well, altitude and height are the same thing. They want to know what is the rate of the height of the pile, how is it changing when the pile is 15 feet high? Friends, the dH dt, that is what they want me to find. They did not give me any information about R. So we want to find a way to eliminate that from my differentiation piece. Well, we know that even though the diameter is what they gave us in the problem, don't we also know that a diameter is equal to 2 radii? And friends, we don't want R's. Why? Because they didn't give us any information about how the radius is changing with time. So how am I going to be able to put that back in at the end of the problem? So I'm going to solve for R. And in solving for R, I can now replace bonehead. I can now replace this R with 3h over 2. And so now I have the volume is equal to 1/3 pi times 3/2 h squared times h, and I no longer have to worry about an R. Now, this is where some kids they're like, I know that the height is 15, but remember that your height is changing over time. So I'm not putting the 15 in now, I'm going to put that in later. So I'm going to go ahead and simplify this formula, and then I'm going to differentiate it with respect to time. Then I will put in my values. So let's clean this up. I have volume is equal to 1/3 pi times 9/4, and then I would have h to the third because I would have h squared times h. Further cleaning this up, this is going to give me 3/4 pi h to the third. So now let's differentiate with respect to time. I have dv dt is equal to 3 times 3/4 pi would give me 9/4 pi h to the second power times dh dt. Let's recall. Now in this problem, notice how since this was a v to the first, we don't have a v that we have to substitute in, but we do know that dv dt is 10 cubic feet per minute. They told us that the height of the cone was 15 and they want us to find dh dt. So I'm going to put this in for 10, 9/4 pi times 15 squared dh dt. dh dt is going to equal 10 over 9/4 times pi. That was kind of sloppy. Let me rewrite that. 9/4 times pi times 15 squared. I've already typed that in to save us a little bit of time here. And so my rate of change of the height is 0.006, and height would be measured in linear feet per minute. Okay, friends, this is up to you, but you could stop the recording if you wanted. This is probably more of an enrichment problem. I don't think any of the problems I gave you are going to be like this difficult. There's some unit analysis, but even though I'm going to call this an enrichment problem, I went ahead and decided to do it. So here we go. I know it makes the video a little longer, but again, at this point, if you're like done, stop. If you are interested, keep watching. All right, an official is watching a race car approach the finish line at the rate of 200 kilometers per hour. Suppose the official is sitting at the finish line 20 meters from the point where the car will cross, and let alpha be the angle between the finish line and the official's line of sight to the car. We'll go ahead and just make that theta. Every year that like bothers kids, so let's just make it theta. All right, at what rate is theta changing when the car crosses the finish line? Give your answer in radians per second. That really is what like throws this problem into a tizzy. The rest of it's not too bad. Okay, so here's what's happening. Car race. Car is driving down and there is a finish line. Okay, so you've got a car. Yes, this is a bad car. Driving down. All right, and they tell you that the car is driving at 2 kilometers per hour. So we're going to have to define this value, and I defined it as x, so that makes that rate my dx dt. Now, you have an official that is 20 meters from the point where the car will cross. So right here, this is where the official is at. The official is 20 feet from where the car will cross. So if I am the official, and yes, this is a pretty bad stick figure, the eye of the official is looking at the car as the car keeps getting closer and closer to the finish line. So what that creates is a right triangle. So let me just erase this and redraw it all nicer. Okay, so this is the car. This is the finish line. This is the official. And this is his line of sight to the car. The question is asking for, and let theta be the angle between the finish line and the official's line. So here is where my theta belongs. And this is important. As the car gets closer and closer to the finish line, theta is getting closer and closer until it's finally 0. Keep that in mind. All right, here we go. So we know that this distance from where the car finishes to the official is 20. And so this is an adjacent side. This is an opposite side. So we're going to pull a tangent. The tangent of theta is equal to x over 20. I can think of this as the tangent of theta is equal to 1/20th x. So when I differentiate both sides, I get that the secant of theta is equal to 1/20th. But we had to do this with respect to time. So that means I have to include a d theta dt, and that is going to be a 1/20th dx dt. All right, so let's move that over here in the middle. Okay, so let's figure out what's going on. We know that our dx dt was 200 kilometers per hour. So let's fill that in. All right, so we know that the secant squared of theta times d theta dt is equal to 1 over, this is going to be 20 meters, times 200 kilometers per 1 hour. So if I want to solve for d theta dt, you have to divide by the secant squared of theta. But when I divide by the secant squared of theta, can't I represent as that's going to be the same as multiplying by 1 over the secant of theta? So I can say that d theta dt is equal to 1 over 20 meters times 200 kilometers per 1 hour, and instead I can call this the cosine of theta. All right, well, think about this. The question is asking for at what rate is alpha changing when the car crosses the finish line. When the car crosses the line, then if this is the official, here's the finish line, and here is the official's line of sight. When it's crossing the finish line, theta is 0. So what is the cosine squared of 0? That is equal to 1. All right, so ultimately, if the question was not asking for specifically radians per second, you could absolutely give me that d theta dt is equal to 1 over 20 meters times 200 kilometers per 1 hour, because cosine squared of theta is 1 when the car is crossing the finish line. Theta is equal to 0, causing the cosine at 0 to be 1. The rest of this is unit analysis. We want to get in radians per second. All right, so here we go. I have d theta dt is equal to 1 over 20 meters times 200 kilometers per 1 hour. I need to get to radians per second. This is where kids sometimes fight. Like, why can you do it? Because you can. And think of science. I know that Mrs. Wilkie isn't here anymore, but Mrs. Wilkie used to tell me, you know what? Because you can. I can just introduce a new unit of 1 radian over 1. I can do that. Okay, so now we have to get all of these meters and kilometers out, and we have to convert the hours to seconds. So let's get a new color. I have d theta dt is equal to 1 over 20 meters times 200 kilometers over 1 hour times 1 radian measure over 1. Well, I do think that the hours to seconds is not difficult. I know that I want to put 1 hour up here so that I can get the hours to cancel. And 1 hour is 60 minutes. And in those 60 minutes, it's 60 seconds. So that's going to be over 3,600 seconds. So in doing that, it is going to allow me to get the hours to cancel, and I'll be left in seconds. So I'm getting close to my radians per second. But I have to multiply to get all of my kilometers and meters out. So we also know that 1 kilometer is equivalent to 1,000 meters. Why did I do it that way? Because then the meters cancel and the kilometers cancel. So what I have left is d theta dt is equal to 200 times 1,000 radians. That's what I have left up top, all over 20 times 3,600 seconds. And I already went ahead and typed that in. So I have 200 times 1,000 over 20 times 3,600 for my unit analysis. So this means that the angle of the sight of the official as the car crosses the finish line, d theta dt is equal to 2.7 radians per second. I hope you enjoyed, and your assignment, your recommended assignment after this video is to do the related rates worksheet. That is what is recommended. And then you have WPE number 5 due not tomorrow, Tuesday, but due Tuesday, April, what date would that be? Let me look at my calendar really quick. I don't have that memorized. I'm so sorry that this is taking longer. Hold up, wait a minute. How about April 7th? There we go. It's due April 7th. Make sure that a reminder, 11:30 on Zoom for office hours every day, and enjoy.